Hello and welcome to this lesson in quantitative reasoning. Today we're going to look at the idea of contradictions, tautologies, and implications. This is a follow-on to our work with truth tables for compound statements with the negation, conjunction, disjunction, conditional, and biconditional. So this is kind of wraps this all together. And it actually points out some statements that provide interesting conclusions. So the first statement we're going to look at is simple. There's one letter involved. There's one statement involved, P. So 2 to the first, that means I get 2 rows. And if there's 2 rows, the 2 choices are either true or false. So I'm doing P and, remember this is the symbol for and, you draw a line across it, so it's a conjunction, P and not P. So the rules for and are both the left and the right have to be true for this statement taken as a whole to be true. So in the first row, I have the left is true and the right is false. In the second row, I have the left is false and the right is true. So both cases come out false. We call that a contradiction. Saying P and not P, I am going to the store and I am not going to the store. It's contradictory. That makes no sense at all. It's kind of nonsensical. But if all of the outputs and the output in the final column of your truth table are false, we call that a contradiction. And in this case, a statement, they call it a self-contradiction. Some other books just say contradiction. So now consider the statement. What if I just change this one thing? I change it to an or. An or is a little kinder in that it lets you, only one of them has to be true. Again, we only have one letter involved, P, so we just have 2 rows. P is either true or false, and then when P is true, not P is false. P is false, not P is true. Now, P or not P, if one side is true, the whole thing is true. Well, in the first row, that side is true, and the left side is true. In the second row, the right side is true. This is what we call a tautology. It's kind of a big word, but it's nice that it begins with a T because it means the values are all true in our final column. So there's a couple of definitions there. There it is right there. Now, P and not P or P or not P are not the most interesting compound statements that make tautologies or contradictions. There will be others. So let's look at this statement. P or Q and not Q implies Q. So you put all this together, and really it's the same as saying Q is what they're saying. So to construct the truth table for this, it's going to be made up of simple statements, P, Q, and the components, not Q, P and Q. So we've got, again, just 2 letters involved, P, Q. Even though this is a not Q here, it's still a Q. So we're going to have 4 rows in our truth table. And it's going to look like this. I think it's in the next slide. I get myself a little lost here. So again, when you have 4 rows in the truth table, 2 statements, your inputs always look like this in this order. Alphabetical order left to right for the P and the Q, then true, true, false, false, true, false, true, false. So we wanted to show this big statement over here. So it's nice to break it up into the pieces. I see I'm going to need a not Q. I see I'm going to need a P or Q. There's not Q, just the opposite of Q in each row. Q is true. Not Q is false, not Q is true, and that repeats there. Then I'm looking at P or Q. I don't need the not Q column, I'm looking right there. P or Q, if either is true, it's true, and the bottom one is false. That's your standard P or Q truth table. And then I'm going to label this with a 1 and label this with a 2. I'm taking column 2 and anding it with column 1. So it's an and. So if both these columns I have labeled 1 and 2 are true, it's true, otherwise it's false. Column 1's false there, so I get a true in the second row, and all the rest are falses because you have a false in one of the 2, the left or the right side. So that's this whole piece right here. That's what I've just done, and we'll call that column 3. So now column 3 is the left side of an if-then. In column Q is the right. Sometimes when I'm doing a conditional, because this is the one that ordered matters, I like to write down the values So I'm gonna write down the value of the left on one side and the value of the right on the other. So the value of this, which is just contained in this blue box, is this column right here that I'm pointing to. So I'm just going to repeat that so I have it right in front of me next to the truth table. That is the left side. That's the value of the left side of my arrow. And the reason I do this is Q is over here. If I just look true then false, then I'm looking in the wrong order. I want to look in the right order. So I'm just going to repeat column Q here. That looks like that's a true, false. That was the one that alternated, true, false. So now I have my left and my right, and I see the answers are already there. And I'm combining them with an if-then. If the left is false, I automatically get a true. So that would cover these three. Now, if the left is true, oh, wait a minute. This does not seem right. If the left is true, I should get a true here. Is that correct? True, then false should be false. This is the case that's false. They use this as an implication, but what they really should have said is not Q. That's the only way this would have worked. No, it's not. It wouldn't even have worked that way. So this actually is not a tautology. It's not always true from what I can see, unless I've made a mistake. False, true, false, false. And it's definitely the case. Now, is this true? Yeah, that is true. So I have a true on the left and a false on the right. This is not a tautology or an implication because this should actually be a false. If this entire column here under the if-then had been true, we would call it an implication because it's under an if-then, but it's also a tautology. A conditional, or they say biconditional statements of tautology is also called an implication. But it's just, this should have been true. In this case, it wasn't. This Q here was false, and this was a true, so this statement actually is false. So this wasn't a good example of a tautology. So an implication is a conditional statement that is always, that all your final answers are true. So is the following statement a self-contradiction, tautology, or neither? So either they want to know if you get all falses, you have a contradiction. If you get all trues, you have a tautology. If you get a mix, you have neither. So we're going to do P. So there's just P and Q. There's a not Q, but there's just two statements. So I've got my 4-row truth table. Remember, if I had 3 statements, I'd have 8 rows. The first thing I do, see, I probably would have done it in a different way. I would have written that first. So P, if and only if Q, that's true when the two sides, the left and the right, match. So it's true here, and it's true here. The other cases are false. I made a column for not Q because it's there. So for this piece here, I'm doing a biconditional with P, not Q. Now, I need to see if they match. So they don't match as a false and true, so that one's false. Here they match, so that's true. Here they match. They're both false, but they're the same, so the biconditional is true. And here I have a true on one side and a false on the other, so that's false. So that column seems correct. Then this column is, let's call this column 1 here and call this column 2 here. This is column 1 or column 2. And notice I wrote the word or because that sticks in my mind as to, okay, that means if either of them is true, it's going to be true. So I'm looking at these two columns here. I have a true there, so that's true. I have a true there, so that's true. I have a true here, so I'm looking at this, one of them is true, this, and then this, one of them is true, this and this, one of them is true, this and this. So this is a tautology because the final output was entirely true. Okay, and we're going to take a look at one more example. So again, we've got two statements, PQ, not P if and only if Q, and it is false that, or the negation of, not P if and only if Q. So I just really quickly think this is going to come out to be a contradiction because I have something and the negation of the same thing. One of those is always going to be false. So when I end them together, I'm always going to get a false. But let's do it out a step at a time. I have not P if and only if Q in both of these parentheses. So I definitely want that. But before I do that, I want to make a column for not P. Not P is false. That should be false. There are mistakes in these slides that the publisher gives me, isn't there? False, false, true, true. And then not P if and only if Q. In this case, not P is false if and only if Q. So I'm looking at these two. They have to match. That is a false. False, false. That is a true. It's almost like they have these exactly backwards. That's a true. And that's a false. So I've got those two statements going on. So that's a false. The negation of that will be true. They did have it exactly the opposite. True, false, false, true. And that will be this piece here. Forget about that. That's wrong. Forget about that. That's wrong. And then I'm ANDing these two together. Every row has one true and one false, so they're all false. They did these two backwards. What they did was they swapped these when they typed it in. But you can see I always get a false. So there's a mistake in the slide for this one. I'll try to see if I can't fix that and put it back correctly in the slides, but it's correct now in the video. So that's the idea of a self-contradiction is all falses. A tautology is all trues. An implication is an if-then or an if and only if that comes out all true. This would not have been an implication if it was all true because it results from an and. That's a subtlety. That shouldn't hang you up too much. Maybe some of the vocab in the homework will show up like that, though. All right. Thank you for joining me for this lesson in quantitative reasoning, and I'll see you in class.